The Large Hadron Collider, or LHC, is the largest particle accelerator in the world, located in Geneva, Switzerland. There are 4 major particle detectors in the LHC. These detectors allow us to observe elementary particles that help us get a better understanding of the nature of our universe and the laws that govern it. Let's take a closer look at the ATLAS detector and learn more about the detection of elemental particles. It all starts with protons. Protons are made of quarks and are held together by gluons. Every second, 2,500 bunches, each made up of 100 billion protons, are being accelerated to nearly the speed of light and fired at each other. When the 2 bunches meet, most protons miss each other, so of the 100 billion possible proton-proton collisions, only around 16 proton pairs actually collide. However, the bunches cross every 25 nanoseconds and are being reused for several hours. During the collision, the quarks and gluons inside the 2 protons interact to form a wide array of particles. To which particles a particle decays depends on probability. The branching fraction, the probability that the collision results in a top quark, is 0.000015%. But what is the top quark? To get a better understanding of this, we first need to take a look at the Standard Model. Currently, the Standard Model is the best theory to describe elementary particles. We can divide all known particles into 3 fundamental categories: the leptons, quarks, and bosons. The top quark is the heaviest elementary particle in the Standard Model. After being formed, the top quark decays into a W boson and a bottom quark. This happens almost instantaneously, namely in a trillionth of a trillionth second. Thus, we can never detect the top quark directly, but only by its decay products. So let's take a closer look at the bottom quark and the W boson. To which particles they in their turn decay is also a matter of chance. The different ways it can decay are called channels. By choosing the right channels, we can reverse engineer the decay process to know if it originated from a top quark. In deciding which channel to choose, 2 things have to be taken into account. Firstly, the channel must happen frequently enough to rule out as much statistical uncertainty as possible. Secondly, it must be easily distinguishable from background events. Keeping this in mind, let's take a closer look at the signatures. Quarks, such as the bottom quark, will hadronize. Hadronization does not result in a clean signature and makes that particular channel useless in detecting the top quark. The W boson can decay in a pair of quarks and a pair of leptons. The quarks are useless because of hadronization. The leptons, however, will take separate paths, and these have a clean signature and can thus be used to indicate top quark production. During our project, we searched for the production of TTZ, which is a top quark and an anti-top quark, and a Z boson, as a result of head-on proton-proton collisions. For this, we used simulated data based on theoretical predictions of the Standard Model.